Hello everyone, welcome to Crypto Innovation Webinar Interview Series. I'm your host Shravani. Today we are in Season 3, Part 5 and topic is very interesting. Byzantine Agreement Past, Present and Future. Over 40 years ago, Peace Sastok and a Turing Award winner Lamport introduced the Byzantine Agreement problem through an exciting story that includes kingdoms, war, and betrayal. This excitement hasn't died out. In fact, thanks to cryptocurrency and the blockchain technology, there is every indication that this excitement is likely to persist well into the future. In this talk, Professor John will present a few foundational ideas that undergird this problem, give a brief overview of Bitcoin, and also provide some thoughts on how Byzantine fault tolerance will continue to play a role in future. Before starting the discussion, let me introduce Professor John. Professor John Augustine earned his PhD in Information and Computer Science in 2006 from the Donald Brent School of Information and Computer Science, University of California, USA. In 2011, he joined the Department of Computer Science and Engineering at IIT Madras, where he is currently an associate professor. Prior to IIT Madras, he spent 2 years as a scientist at Tata Research Development and Design Center, Pune, India. His research interests are in designing and analyzing algorithms, especially randomizing algorithm for distributed computing environments. Inspired by recent development in distributed ledgers, cryptocurrency, and other distributed trust applications, he has been interested in various aspects of Byzantine fault tolerance. Welcome, Professor John, to Crypto Innovation Webinar Interview Series. And thank you so much for accepting the invitation. Stage is all yours, sir.
Thank you. Okay, so I need to.
I'll just hand over the presenter right to you. Did you get it?
Yes. Is my screen visible?
Yeah.
Okay. Keep that. Okay, so thank you, Shravani, for the warm introduction. Without further ado, let me get started. I want to just briefly emphasize something that is important for us to notice. There are networks all around us. It could be communication networks, information networks, social networks, biological networks. Many such context networks arise. And what is it that makes a network a network? If you deconstruct it, there is two essential aspects to networks. You have what I call decision makers or nodes, depending on the domain, could go by various names. These are like the key elements of networks. And these key elements are connected by links or edges. So that's what essentially is a network. So you have a variety of examples that you can look at. And each one of them, for example, if you look at the brain network, the nodes are the neurons, and these neurons connect via dendrites, axons, and synapses. And a common theme for a lot of these networks is the following. The actions or activities are local, but there's global phenomena that arise out of these local actions. Just to give you a sense of the network, so one important aspect is communication. So you have these local nodes making decisions, but they don't make decisions in isolation. They interact with each other, and they communicate with each other, and then based on information that they receive, they act. So communication is key here. And communication happens in multiple ways. So let me just list a few options. And out of that, for the purpose of this talk, I'm going to pick a few. So for example, communication can be synchronous at one extreme or asynchronous at another extreme. For synchronous, the assumption here is that there is some sort of a a music conductor who's giving the timing and saying this is the start of a round, so everybody sends their messages. Now they send their messages to their neighbors, and then they receive messages that their neighbors sent, and then they process the messages. That's one music beat, if you will, or in this context, we will call it a round or a time step. And how do we actually send the messages? That could be, I mean, just to be clear, on the other extreme, there's also the asynchronous setting where there's no music conductor, if you will. Messages take arbitrary amount of time to reach from one node to another. And that's a fairly complicated setting. So we're going to stay away from that for the purposes of this talk. We're going to stay in the synchronous world, and there's intermediate assumptions as well, called partial synchrony and semi-synchronous and things like that. We're not. I just want to let you know that there are those options, but we're going to focus on synchronous networks. How do you communicate? You could possibly communicate by shared memory because everybody looks at the same whiteboard or something like that. But the way that we're going to do for the purpose of this talk is by passing messages. If you want to communicate to a neighboring node, you create a message with information in it, and you pass that message to that neighbor. And this is how most networks work because there is usually not some common shared memory. Then there are these alternatives. Sometimes you may be able to say something that the entire world hears. That's broadcast. The other option is point-to-point. And we're going to mostly assume point-to-point, but actually for some things, we're going to assume broadcast as well. Okay. So, and then there's the option of private channels versus full information. This goes into the aspect of security. Suppose, and we're going to talk about Byzantine resilient algorithms. So we want to know what level of security we have. Do we have private channels between the nodes? In which case, if I send a message to you, only you and I get to see the message. Or is it the other way where it's full information, everybody gets to see the messages? Now, with private channels, you need to assume some form of cryptography. With full information, where like if I send you a message, others who happen to get that message can also eavesdrop on it. Okay? That's the case where I don't need to worry about any cryptographic requirements. It's a more difficult setting to be in, but in that sense, it's also more powerful because you don't rely on any cryptography. Okay, so this is the setting. So we're in the networked world, and this is the way communication is going to take place. And the type of problem we're going to focus on is going to have this sort of global phenomenon coming out of local behavior, and you see that all over, all around us. So if you look at, let's look at this one classic example: the lions trying to attack an animal, a prey. The important thing is these lions will have to be very careful and strategic. They have to communicate with each other and decide whether to attack or not to attack. Sometimes their position might not be good enough, and so the better thing would be to not attack. Or if they're going to attack, then everybody has to attack. If there is a sort of a half-hearted attack, only say half the lions attack and the rest watch, then the giraffe is going to be more powerful. It's going to overcome them and kill a few lions. And so this is a classic case where you sort of see individual decision makers, but a global outcome that has to emanate out of these individual decisions. Okay, so and of course many of our states went for voting recently, right? So that's another example where there's individual decision makers in a democracy, but you want some sort of a global outcome out of it. Okay, and there are many such other examples that you can think of. And the agreement problem is a very fundamental problem because it tries to abstract out the essential aspects of this sort of relationship between local behavior and a global outcome. What is the agreement problem intuitively? There are participants, the nodes in the network, and they all want to, I mean, they have couple of options at their hand, and we represent them in as bits, either 0 or 1, or in this context, I've given them colors, green or orange. And they have to then reach an agreement as to which one they're going to go with. Okay? So they have to agree on one of the bit values. And that is essentially what we saw in the context of this lions hunting a giraffe. So why do we need agreement? This is a fundamental issue in many contexts, but traditionally the context that computer science people mostly studied was in the context of databases, particularly distributed databases, where you wanted to maintain multiple copies of data in multiple machines, replicated copies, and we need to ensure consistency. So the machines must have some agreement about what the data currently is. And this is very important, as you can imagine, in the context of large banking systems. One of the fundamental algorithms of this type is the Paxos agreement algorithm, and it's used by Google and Microsoft, IBM, and so on. So these ideas have percolated into very fundamental systems in the technology world. Going back to a little bit of history, okay? So this problem was first proposed quite a while back, over 40 years ago, by Pease, Shostak, and Lamport. And Leslie Lamport eventually went on to win the Turing Award for this and a few other such very important contributions. And they introduced it in two fundamental papers. And they introduced this in a very interesting way, and in a way that captured our imagination. So they called it the Byzantine generals problem. What is the Byzantine generals problem? You have a city that is under attack, and the attacker. So the viewpoint that we're taking is from the view of attackers. So we have to decide whether to attack this city or not. But our army is now split into multiple groups, each having a separate general. Okay? So each general has their own army. They have to kind of coordinate with each other and decide to attack or not. Okay? And they can communicate by passing messages. And they have two choices, either attack or retreat. This is very similar to the hunting game that we saw a little while ago, right? And the generals have, there's a twist to the whole story. This is, as of now, it's reasonably straightforward. You can basically look at, okay, so how many generals, you can do a voting. You can vote and say, okay, let's look at if there are 7 generals, 4 of them want to attack, 3 of them want to retreat, then we'll go with the majority. But the twist in the story is that some of the generals are traitors, and they can provide a lot of misinformation, or the common sort of the popular term these days is they can produce fake news. They can misinform you and therefore foil the agreement and lead to a situation where some good generals attack and other good generals retreat. And this whole thing will mean that the attack will be weak, and so the city will be able to survive the attack. And from our point of view, from the army's point of view, we will end up having a lot of casualties. So this is the kind of story that they use to illustrate this problem, and it has really captured the imagination of computer scientists, because this sort of interesting story is just so nicely captures the fundamentals very well, and it's something that is still being applied, right? So we'll talk a little bit about how it is relevant in today's context as well. But before we move forward, let me state the same problem, but in a slightly formal way, so that we will be able to understand the details a little bit more carefully. let's say that, so now let's assume that there are n generals. So we've generalized it to n generals or parties or nodes. Use your favorite term here. And an unknown set, this is important, an unknown set of generals are traitors. The T of them are traitors. Okay, so think of n being 100, T being some 10. Like 10 generals out of the 100 are traitors. And now each general to themselves, based on the information that they have, they propose to either attack or retreat. Okay, and now they're allowed to, at this point, so this is the initial conditions. Okay, after the initial conditions, now they're allowed to communicate with each other. So the goal of this communication is to reach a point where they achieve these requirements. What are these requirements? First of all, that they must reach an agreement, meaning they must, all the good generals must agree to either attack or retreat. Okay? And you may ask at this point, okay, you're not talking about the reason behind attacking and not attacking. And that's something that this problem is sort of abstracted away. We cannot go into the specifics of, when you should attack and when you should retreat. You have to assume that when the good generals propose something, they have done their homework. Okay, and that when a good general says attack, that means he really sees a good reason to attack. And when a good general says not attack, retreat, then also there's it's based on some good understanding of this situation at hand. So now, how do we ensure that the agreement is a useful agreement, is a valid agreement? The idea is this. Now, whatever decision you make, you have to ensure that at least one good general actually proposed that idea. Okay, either if all, another way of stating it is this: if all the good generals said attack, you must attack. If all the good generals said retreat, you must retreat. Okay? But if some of them said attack and some of them said retreat, then it doesn't matter which one you choose, because presumably both have good value to it. Only thing is, now at this point you must reach an agreement. You cannot have a half-hearted, half of you attack, half of them don't attack. And of course, you want these decisions to be made in a timely fashion. So termination within a finite amount of time, that's also important. Okay, so this is the basic problem. And let's look at a bit more about it. The main challenge comes from the fact that you have some traitors. Okay, now the traitors, their behavior is controlled by an adversary. In colloquial terms, it's a bad guy who's sitting there. This is like the handler. In spy movies and things like that, you have a handler who's controlling all the spies, right? Or you have this handler who's controlling all the bad generals. He's the one who's paying them off, and he is the one who's controlling all the behavior of the bad generals. Okay? So this adversary controls the behavior of the bad nodes. We sometimes use the word Byzantine nodes or malicious nodes or adversarial nodes. These are bad guys. Okay? The bad guy, this is, we're going to be a little bit careful here. The adversary is like this handler, right? The actual nodes, there are some actual bad nodes, but then the adversary is one guy who's actually seeing all of their behavior and controlling them. So in some sense, another way of saying it is he's acting like a common decision maker for all the bad nodes. Okay? Now, how powerful is this guy? So we have, in this problem, we have to define the power of the bad guy, because based on that, the algorithms will emerge. One extreme case is where the bad guy is adaptive, meaning he can halfway, as the communication and the protocol and the algorithm are executing, he can decide who becomes bad and who remains good. Okay? So that's what is called an adaptive adversary. The non-adaptive case is he has to decide ahead of time who's good and who's bad. Okay, and then he gets to control all the bad guys. Rushing is when, like, for example, the good guys send their messages, and then this adversary gets to look at all the messages. Remember, we're in the full information model, so all the messages, we assume that the bad guy is actually able to see all the messages. He gets to see all the messages and then decide what the bad guys love to send. Okay? So that's a rushing thing. So he gets to see everything and then rushes in with the messages sent by the bad guys. The non-rushing is the case where he doesn't get to see it. Okay? So you can sort of see that there is a sort of a rich set of ways in which you can define the problem. So now let's actually start getting into the problem, and we can ask some fundamental questions. So remember, we said P nodes are bad. Now, what are some fundamental limits? And so, in other words, how many Byzantine or malicious nodes can be tolerated ever? Okay? There's a fundamental limit here. Byzantine agreement is impossible if P, the number of bad agents, is more than n/2, even with PKI. PKI is basically public key infrastructure, and just assigning, having a certifying authority giving identities to each of the nodes. So even if you have this sort of extra power with a little bit of central control, still Byzantine agreement is impossible if the number of bad agents is at least a half. And it's a fairly simple argument to see why this is the case. It's going to be, we can use a quick indistinguishability argument for it. So quite an interesting, simple one. So let's assume that you can actually handle n/2 Byzantine nodes. This is for the sake of contradiction. What you do is you take there are n nodes, right? You split them up into two sets of equal size. Okay, and you consider two different executions. The first execution is where you give 0 to the first half, 1 to the first half. So the first half of the agents, they're all good, by the way, in this execution. The first half all have zeros. The second half all have ones. And remember, no corruptions, no bad guys here. And so let's say, then the protocol has to run, and there must be some agreement. Remember, agreement is the first requirement of this problem. Right? So they will agree on some value, either 0 or 1. Okay? So let's, without loss of generality, let's assume that they agree on 0. Okay. Now let's look at the second execution. In this execution, again, you split the group into two, the nodes into two groups. In this case, both groups start with 1. Okay. So remember, all the nodes start with 1. So the agreement, by validity property, everybody must agree on 1. Okay. But here's what the bad guy does. He corrupts the set P0, the first group, the first half. And all he has to do is tell each of these corrupted guys to behave like the guys, the set P0 under execution 1. And so look at it from the point of view of nodes in P1. They will not be able to tell the difference between the left execution and the right execution. The left execution tells us that the decision has to be on a 0. The right execution, these guys, what will these guys do? Since that's all the information they have, they will decide on a 0. And that's exactly the wrong decision, because by validity, if all the good nodes proposed a value, remember in this case, they proposed the value 1, then their decision must be on the value 1. Instead, they are deciding on 0. Okay? So this is the key idea by which you can argue that it's impossible to reach agreement when P is at least a half of the total set of nodes. Okay. So this is the theorem. This is well known, okay, for like almost 40 years. There is another fundamental limit, this time without PKI, without the sort of without a certifying authority. The limit is 1/3. So now, without a certifying authority, the algorithm is weakened a little bit, which means that our ability to tolerate bad nodes is further weakened. We can only tolerate uh, fewer than 1/3 bad nodes. Another way to state this agreement is not possible if at least 1/3 of the nodes are bad. So again, this again requires an indistinguishability argument, and I'm going to give the key idea here. We're going to just focus on the case where there are 3 nodes, okay? And one of whom is bad, and we don't know who is bad. The general case for arbitrary values of n will fall out as a consequence. It's a nice homework to think about. I'm not going to talk about that now. So you look at these 3 nodes. You have these 3 agents: P1, P2, and P3. P3 is, let's say, corrupt. The 2 good nodes are starting with 1. The one within brackets is the starting value. By validity, they have to agree on the P2 must have output 1. What about execution 2? This is a second different execution, same set of 3 nodes, but this time we make P2 the bad guy. P1 and P3 start with the values 0. Okay, so and here in the first execution, the bad guy P3 was P3, and he acted like he had a 0 with him. In execution E2, P2 is the bad guy, and he acts like he has the value 1. But again, because we are assuming that this protocol is correct, the output should be a 0 because the 2 good nodes are proposing 0. Okay. Now comes the twist. Let's look at the third execution. Now the bad guy is P1. Okay. What he is going to do is he's going to act like his value is 1 to P2. He's going to act like his value is 0 to P3. Now, if you look at the picture here, let's look at P1, rather P2. P2's picture looks exactly like P2's picture in E1 because he has 2 neighbors. His own value is 1. His one neighbor is saying 1, another neighbor is saying 0. So if he'll therefore follow the essential output of E1. That output is 1. Whereas look at the P3's execution, his viewpoint, his world view looks exactly like P3 in execution 2. Why? Because his value is 0. One of the neighbors is saying 1, the other one is saying 0. That's exactly the viewpoint that he has in execution 2. So what will happen? P2 has the view, same view as in E1. P3 has the same view as in E2. And so they will reach different agreement values. Okay. So this is a problem. It's a fundamental thing. You cannot reach agreement if the number of bad nodes is at least 1/3. So it has to be fewer than 1/3. And in fact, even back in 1982, Lamport, Pease, and Shostak, they gave a solution that will work as long as the t is less than n/3. But it's it's not a very good solution, and that's why you had 40 years of improvements over that. It takes very large messages, a large number of messages. Basically, it tries to hear messages through every possible path from source to destination, and then tries to figure out who the traitors could be and who the good nodes could be, and then somehow tries to reach agreement. So that's it's a very impractical algorithm. Okay. So step back here. So you may ask, this problem doesn't seem that difficult. Maybe why not we just go with majority? The problem with going with majority is this. So let's take the very simple 3 nodes case. Why the majority fails? So the majority fails. The idea behind why the majority fails is this. Let's say you have A who's proposing 1, B who's proposing 0, and there is an agent in the middle who's bad. What he will do is he will propose 1 to A and 0 to C. And so A will therefore be inclined to decide on a 1, and B will be inclined to decide on a 0 because they're both going by majority. But in reality, that's not a good decision because there's going to be disagreement between A and C. So majority is not a good approach. In fact, you can generalize it not just for 3 cases, 3 nodes. It generalizes for a large number of nodes as well. Okay. Why? Because the key problem here is that the bad nodes can lie about their values to different nodes. They can a bad node can tell me that it has 1 and tell you that it has 0. And so we'll be working with fake news. Okay. So the question is how to defeat such a powerful adversary. The power comes in randomization. If you can toss coins, then you have a chance to win over the adversary more efficiently. So let's what is a coin toss here? I mean, a randomization here. You just basically you assume that each node has a coin in its pocket, and whenever it needs random bits, it can just toss the coin and gets heads or tails, and based on that, it can get random bits. That's the idea. So let's look at, and when if you can generate 1 random bit, you can generate any number of random bits, and so you can choose random nodes. You can generate random structures. Okay? So let's look at a very simple algorithm that actually works. So this is a very simple algorithm that works. Remember, each node starts with an input value, either 0 or 1. You repeat the following log n times. Okay? So what do? Each node basically does some random sampling. It picks 2 other random nodes, okay, and gets their values. Remember, it can be good nodes or bad nodes, we don't know. It picks 2 random nodes and says, okay, can you give me your value? Can you give me your value? Picks those 2 values. And then what it does is applies what is called a majority rule. So remember, it randomly sampled 2 nodes. It has its own value as well. So it now has 3 values. So there's going to be 3 bits, right? And so one of the bit values, either 0 or 1, is going to appear as a majority value. So in the next iteration, your vote is going to be that majority value. Okay? So initially you start with your original vote, but each time when you sample, you go with the majority between the 2 that you sampled and your own. What is nice about this algorithm is it's very, very simple and very, very efficient. What is not so nice is that it can only tolerate square root of n Byzantine nodes. So if there are 1,000,000 nodes, it can only tolerate about 1,000 bad nodes. That's the weakness of this algorithm. But on the other hand, it's extremely easy to implement and very efficient. Okay. What's the idea? So you may say, okay, it seems a little strange. This random sampling somehow will reach agreement, or why is that? The idea is this. You have to first notice that the worst case for this algorithm is equal number of zeros and ones. Because if there is an imbalance, okay, the number of ones, if in the scale, if this arrow points to the number of ones by the good nodes, then what happens is this algorithm will quickly terminate. Why? Because most of the samples will come as ones, and so all the individual nodes will start voting more and more for 1, and it will quickly there'll be what's called a strong drift towards agreement. And the same thing will happen if the number of ones is very small, and the drift will happen on the other side. The bad case is when it is somewhere in the middle. Okay? Why is that a bad case? Because remember, there are square root of n bad nodes, right, they can lie about their values. So they can actually make things, I mean, they can bring it back to like this perfect center. And if they bring it back to this perfect center, it's hard to decide. And here's another important thing you have to keep in mind. They can lie to, I mean, they can misrepresent their values in multiple ways, right? So they can tell me that they have a 0 and you that they have a 1. So we'll be counting things differently. So it becomes a mess. It's a lot of confusion. Okay? But what is our saving grace here is that because there are only square root of n Byzantine nodes, just by, if you're in this middle zone where there is roughly the same number of zeros and ones, there is just by the sampling, what happens is there's a standard deviation of square root of n by which you will fall out of the bad zone. And that will happen with constant probability. So with some constant probability, you'll fall out of the bad zone, and then the drift will take you in one direction or the other. So that's a rough intuition. There's a lot of detail there, but that's the rough intuition. Another nice idea that, I mean, so this idea is great, but the limitation, because of its dependence on the standard deviation, can only tolerate square root of n bad nodes. What can you do if you want to tolerate more than square root of n bad nodes? So, our goal, remember, is to get closer and closer to that holy grail of n over 3 bad nodes, fewer than n over 3 bad nodes. So now the approach, so now I'll give you an approach that can tolerate up to some fraction, say 10% bad nodes, but this will assume that there is a global coin. So what does it mean? It's no longer a coin that is sitting in individual nodes. This is a coin that the way to think about it is, it's a coin that is tossed in the sky, and everybody can see simultaneously whether it came out heads or tails. So what is how do we use this global coin? The way we do it is the following. We create two different thresholds. Remember, the previous algorithms, the implicit idea is that n over 2 is the threshold. As you move above that, you drift towards all ones. Below that, you drift towards all zeros. In this case, what you do is work with two different thresholds. And every time what you do inside this loop, you count the number of votes, 1 vote. So you try to, you first individually make all the counts. Okay? So if the bad nodes are going to lie, they're going to have to lie in the first bullet over here itself, inside the loop. Then and only then do you toss this global coin. And use this outcome of the global coin to decide whether you're going to use T1 as your threshold to decide on 1 or 0, or T2. So it's a global coin, so everybody decides T1 or T2. So what is this? How do you use this threshold? Basically, you pick the threshold. Let's say T1 is chosen. Now you go back to the counts on the number of 1 votes that you have. If that number of 1 is more than T1, you subsequently vote for 1. Otherwise, you vote for 0. Okay, so that's the simple idea. And the key is to keep these two thresholds sufficiently far apart so that the two thresholds don't interfere with each other. And the nice thing is this. I mean, so in the interest of time, I'm not going to go into details, but the idea is this: the bad guys, the adversary can play games, but it can play games in such a way that it can only target one threshold. It cannot target two thresholds and try to play games against both thresholds. So where the randomization helps is, with some probability, the threshold that actually gets used for the subsequent decisions is going to be the threshold that was not targeted by the adversary. So then when that happens, you quickly, the algorithm picks the correct threshold, correct decisions are made, and then afterwards it becomes very difficult for the adversary to foil you anymore, because you either go into very few ones or a very large number of ones, and then it kind of goes outside of the ability of the adversary to control the situation. So that's the key idea. you may ask, so how do you do this global coin? The key to think about it is it doesn't have to be a perfect coin. You just need it to, it's okay to have some bias, and it can even be completely wrong. You just don't want it to be repeatedly wrong and repeatedly very badly biased. Okay, so if you can elect a leader, sometimes the leader might be wrong, but even if every once in a while you get a good leader who then tosses the coin on behalf of everybody, that's actually good enough. Okay? So what this does is it reduces the agreement problem to leader election problem. Okay, what it means is that out of these n nodes, you want to choose a node that is actually a good node with some probability, and everybody should know. I mean, so the leader must. So all good nodes must elect the same node as the leader. That's important, and the leader must be a good node with some good probability. Doesn't have to be perfect. I mean, so for example, you can never exceed this probability, like T over N, because if this is the kind of probability you'll achieve even if the bad nodes simply don't do anything bad. Anyway, I'll quickly talk about a couple of very nice leader election algorithms and then go into modern stuff. The one idea is this, what is called baton passing. Okay, so I'll shorten these things. Baton passing is simply this. You start with a baton given to an arbitrary node. And then in every round, I mean, just to be clear, this one, I'm doing a little bit of cheating. I'm shifting from point-to-point communication to broadcast here. But there are some reasons behind the scenes. I mean, for simplicity, I'm going to focus on broadcasting here. Now, every node that gets the baton has to pass the baton to another node that has not yet received the baton. Okay? So so you keep on passing the baton. First node that gets the baton has n-1 options, so he will pass the baton to one of them. Okay, all the good nodes will just pick a random node and pass the baton. The bad guys, they can strategize. Okay, the point is this: you keep passing the baton and see who gets the baton at the very end, and that person is the leader. And then that's the idea here. And you can think about why this actually works and all that. But the crucial thing is this can tolerate close to a linear number of bad nodes. It can tolerate bad nodes of up to Cn over log n. It's not perfect, but it's a nice algorithm, a nice idea, and it can give you a good leader with some probability. Okay, so you can think it's a very intuitive algorithm. You can think about why it works, but again, the other problem is it's a little bit slow. It takes O of n rounds because you have to keep passing the baton sequentially. The other beautiful idea is the lightest bin protocol. What this idea does is basically the key idea is this: you create a bunch of bins. Again, you need global broadcast here. You create a bunch of bins, and you ask each node to commit to one of the bins. Okay, so it's like putting myself in one of the bins. So there are n nodes. Each one of them puts themselves in a bin, and they have to commit to that bin, and they have to do it in a public way. So everybody knows who is in which bin. And then what you do is you consider the bin that is lightest, like having the fewest number of nodes that put themselves into that bin. And those are the bin, I mean, the remaining no longer are candidates for leader position. The remaining are the ones. Okay, and you repeat the algorithm based on those remaining ones. The intuition is this: if you are a bad guy, you maybe what do? If you put yourself in a very light bin, what will happen is you can only put so many bad nodes into a light bin, because if you put too many bad nodes into a light bin, it will no longer become light. Some other node will become light. So you kind of it really puts the bad nodes in a difficult situation, and taking advantage of that is this lightest bin protocol. And you keep repeating this, and with some extra little stuff at the very end, you get some very nice results. You're able to this protocol can tolerate close to 50% bad notes. It can do it very, very fast as well. Okay. Really nice algorithm. And so this is the classic sort of results in this thing. But and then since for the last 40 years, there's been a long list of works, and I'm not going to go into details in the interest of time, because I want to talk briefly about what is happening now. I'm realizing that I only have about 5-10 minutes left. So now in the this was very nice. A lot of things happened in the world of agreement. It had a significant impact, but most of the impact was behind the scenes. What really brought Byzantine agreement to the forefront is Bitcoin. This thing that happened in 2008, where this idea of a peer-to-peer cryptocurrency system was introduced by a person or persons by the name Satoshi Nakamoto. This is the famous Bitcoin, and crucially, it is using agreement. Okay? And it's using agreement in a completely different way. The point is, in the context, let me briefly see what the context is. You have a bunch of participant nodes in the internet. They want to transact with each other. So you want to so if two nodes want to transact money in this sort of a setting, you have to normally the approach is you send the money to a bank, and then the bank sends it to the recipient. But you want to get rid of that bank. So what you want to do is you want to somehow put the ledger on the sky so everybody can see a common ledger. Okay? So it's a ledger transaction. Every transaction is recorded, and you want to make sure that the ledger is maintained without any central authority and lots of other nice things. It should be consistent. Nobody should cheat. It should all the transactions should have proper integrity. It should be easy to use. No double spending. So if I have some money, I should only be able to use it once. I should not be able to spend it second time. This was a big issue actually with cryptocurrencies prior to 2008. And of course, it has to be anonymous and should be confidential. You and I, if we are transacting, we should know that we are transacting, but no one else should know that we are transacting. Okay. So the idea is to record all the transactions in a sequence of blocks called a blockchain. And the crucial step in this workflow is that you need to be able to agree on what is the next block of transactions that gets updated into this linear structure called the blockchain. Okay, so that's and that crucially requires consensus. And because of the confidentiality reasons, it is crucial that I mean all the previous blockchain, agreement algorithms, they work well as long as each individual node has a clear identity or has one way that it can operate in the network. But this opens up the possibility of Sybil attacks. What are Sybil attacks? One very powerful server just creating multiple identities. And the ability to overcome Sybil attacks was a big problem. And the way Satoshi Nakamoto overcame this is by using an established idea called proof of work, where every time a consensus is to be made and a block, we have to decide on which block to add to the blockchain. What the consensus protocol requires is everybody should solve some puzzle, okay? And the server that solves the puzzle first gets the rights to add the next block in the blockchain. Okay? So that's the sort of distilled idea behind it. And hopefully not too many servers. Usually it'll be just one server that wins this race and gets to add the next block. Sometimes there'll be what is called bifurcations or forking, where multiple servers will win will think that they have gotten the right to add the next block. So they will start adding their own blocks, and there might be some issues to work out. But really, the crux of the idea is this. And this proof of work is turned out to be very useful, but I'm going to skip a few lines. There are some issues with it. The crucial issue is, I mean, so a lot of good things. Like, for example, it manages to avoid double spending. Let me see if I have some. Yeah, it avoids double spending. No inconsistent transaction will be accepted, first of all. And if there is a fork, you basically have a rule to overcome it. Everybody sees that there is a fork, but they subsequently they will always add to what is currently the longest chain, and they break ties arbitrarily. Soon enough, what will happen is one of the folks will start to speed up just by randomness, and then everybody will start building on that fork, and the other one will be lost. So this is the way in which it manages to handle forks. Simple ideas that work quite well. Okay, but we have to be careful though. What can happen is if you give too much power to the bad guys, then they can do double spending. So let's say the blockchain went up to some point. Focus on one of the transactions, the blue transaction. Suppose you want to undo the transaction. What you do if you're the bad guy is you start creating a separate fork purposely from the block prior to that, and grow the blockchain fast, and assuming you have enough power to do that. And if you become the longest chain, then everybody will start building upon that, and so the blue transaction is essentially lost. Okay, so that's another thing. So this is kind of what led to this principle that you need to make, before you assume that a transaction has succeeded, you need to wait for 6 blocks so that you're sure that that transaction is going to be accepted in the blockchain. So this whole idea of blockchain just opens up a whole host of new things, because it's great, blockchains work, but the problem is this: they consume a huge amount of energy. They're highly computationally inefficient, because there's a lot of unnecessary work that is being done. Energy-wise, it's not very sustainable. And scalability is also poor. It's nowhere near the scalability of the internet. So for something like cryptocurrencies to take form and get used by everybody, you need it to have scale to the level of the internet. Now, I mean, like 30 years ago, only a certain small part of the world used the internet. A certain fractions, only few families could afford it. The internet. Now, with it's scaled to the point where almost everybody can use the internet. For cryptocurrencies to be useful, they have to scale to that level, and they are nowhere near that level. So this is again a big issue to be overcome. And for all of these, efficient agreement and lead election protocols are going to be crucial. So this is going to be where the future is. A lot of work is going to happen in this context. Apart from that, blockchain is a technology that emerges not only for cryptocurrencies, but also for a variety of other applications, smart contracts, maintaining public records of some ownership and things like that. So in general, towards a very decentralized world, that's where blockchains are heading. And it's going to be interesting to see, how agreement protocols evolve to be able to handle this sort of a situation. And perhaps we may need to tailor these protocols according to the application at hand. So yeah, with that, I want to. I think my time has come to an end. I want to thank you all, and particularly thanks to those people whose slides I have used in order to create these slides. So thank you very much. I'm open to questions now.
Yeah, thank you, Professor John. It was indeed a great topic, actually very new to me. This now webinar is open for questions. You can post your questions. Okay, there is a question. How do I reach out to you, John?
Oh, I Augustine at iitm.ac.in. So I don't know if I can type it in here.
So
Oh
it
yeah,
is very easy to reach Professor John on the website, IIT Madras website. So you can
yeah.
easily reach
So
out to
that's
him.
my email
So
address, and just to be clear, my group CCD, cyber cryptography, cybersecurity, and distributed trust. We're actively looking out for people who want to engage with us in various ways. So please do reach out with us to us. So that's my email address, and yeah, if you just, I think if you just Google my name, I'm sure you can find my webpage as well.
yeah, correct. So Vikram is saying this is very informative and very articulated webinar. So yeah, it's definitely is the very informative. So I think any question from the audience? So Professor John, here it is like as you have discussed, it is for bitcoins also we are using. So do you mean to say that Byzantine protocol is now using in Bitcoin?
Absolutely. Yeah, the proof of work is a Byzantine fault tolerant resilient protocol for reaching agreement. So here the agreement is which block should you add to the blockchain. And everybody should agree on the same block, because the blockchain has to grow in a way that everybody has agreed upon. And for that, you use proof of work approach, and that is essentially an agreement protocol. It can handle. I mean, so the point is it will work as long as at least 50% of the computational power is resting on good in the hands of good people.
So is there any attack on this protocol, or have you figured out like in the literature or in this? So are there any
Oh yes,
attacks on this?
absolutely. There's a host of different things. The most common thing is the sort of forking attack that I briefly talked about. So see, here's how it will happen, right? Let's say I pay you some money to buy your car, okay, and that's a transaction gets onto the blockchain, and that's a block. Then so that transaction is recorded in the last block of the blockchain, let's say, and then all of a sudden what I do, let's say I now get lucky. What I can do is I can use the same amount of money and have a different transaction and start a different fork in the blockchain.
Ah,
And then what I do is I try to grow that fork as much as I can. And what will happen is if my fork, this fake fork gets to be the longest fork, then people will start growing on that. And then you would have given me the car, and I would have claimed to have given you the money, but then that little branch of the blockchain will be nullified, and so the
nullified.
money you will not receive the money. You will not be able to use that money. So that's the attack.
Yeah.
That
So you're
forking attack is the most common form of attack. And then there is a lot of other attacks. Like the one that I'm particularly concerned about is a little bit deeper. It's in the fact that the underlying thing in the Bitcoin network is actually a peer-to-peer network. And there, what can happen is some good nodes can get eclipsed. What that means is they can just get hidden by a layer of bad nodes. And so all information to and from those nodes can only be through bad nodes, and that can lead to a lot of problems as well. So these are called eclipse attacks, and
eclipse.
that happens at a slightly deeper level, at the network level. So that's
So
another
you have
form, and there
talked
are
about
several
some.
others.
Yeah, so you have talked about the normal distribution. So can you apart from this, any other distribution will play the role over there, or it will be always normal distribution?
Oh, it'll be the normal distribution mainly because in the context where I used it, it's basically this comes up in the following way. You have each node sampling two nodes. They get their two values and my own value, and then you take the majority. So this is essentially is a sample. What it gets you is basically a randomly sampled value with a bias that is in proportion to the number of ones in the system. What that ends up being is the binomial distribution. And
Yeah.
And the way to analyze the binomial distribution is one way to do it at least is to approximate it to the normal distribution, because the binomial distribution will have it will have the nice bell curve shape. Mathematically also you can do it precisely, but intuitively it will have the nice bell curve shape which exactly follows a normal distribution for large enough values of n. And so you can, I mean, I was using the normal distribution, assuming more people will be more familiar with that. And there, again, the standard deviation shows up and you kind of get kicked out of that middle bad area. So that's the idea.
So there are a couple of questions, there are a lot of questions. So any framework for this?
Framework for it, it actually changes a lot. As you can imagine, agreement in the Bitcoin context would be one way to think about it. Agreement in the there, you know, in the Bitcoin world, it's completely anonymous users. But on the other hand, agreement also gets used inside companies like Google, and I mean, like Paxos is an agreement algorithm that gets used inside Google and Microsoft and all those places. There, the nodes are not anonymous. They are controlled by the organization. So the framework will be different there. So there is no one common framework. There's a lot of variety. And so if you really want to get into this area, then at least at the beginning, you should probably decide on one application and try to follow the framework followed by that application. This I'm addressing to students who may be considering this area. And of course, once you get used to it, then you can start diversifying into other areas.
So one more question is, how do you see quantum algorithm resistance for PBFT?
I do not know enough. This will be an excellent question for my colleague Shweta Agrawal. She and I are the ones who started this group CCD. If you have not called her yet, you should call her and ask her to give a talk. I do not deal with quantum at all. So she is squarely into quantum cryptography. I really think she should answer that question.
So I think definitely with your recommendation, I would like to call her in Crypto Innovation Series. So there is one more question. Newer cryptocurrencies like Pi coins, they promise to solve the problems of energy usage. What is your view of them?
Yes, so they use a variety of different schemes. One scheme that seems very promising is proof of stake. So proof of work is somebody gets the authority to add a block to the blockchain, and you prove that ability by having done some work, by solving some puzzle. Proof of stake is a little bit different. You do that by based on the amount of cryptocurrency that you actually own, your stake in the system, so to speak. And that is helpful in a lot of ways because now you don't have to do a lot of hard work and prove yourself by solving puzzles. Everybody can see by looking at the ledger, you can sort of see who owns how many bitcoins or whatever the currency might be. And so then you can sort of figure out who has most stake, and then you elect a leader based on the amount of stake. So the probability of you being elected the leader will be in proportion to how much stake you have in the system. And this is turned out to be a useful way to reduce the amount of energy, because the proof of work, that unnecessary solving of puzzles is not there. Having said that, it comes with its own bag of problems. One is now all the power rests on the so-called rich who have the stake. What about those who do not have the stake? What kind of say do they have? And the other thing is, what about applications going beyond cryptocurrencies. Cryptocurrencies, yeah, everybody knows who owns how much, but it's harder to implement something like this in other contexts where stake is harder to measure. So that might be one issue. Another big issue is proof of stake is one step in the right direction, but in terms of scalability, none of these things are scaling to the level of anywhere close to the internet. They are all having about 10,000 participants or something like that. Even Bitcoin network at any point in time supports about 10,000 participants. That's the oldest, most established cryptocurrency. So being able to scale to these larger levels is going to be a challenge that needs to be overcome, and that's in a sense it's there is a small. I mean, in terms of attention in the world, cryptocurrencies are in a lull. People are not sure what's going to come of it, but that's actually a very good news for researchers, because without all the hype, we can sit down and think about what will work, what won't work, and all that. Not worrying about the hype, but just worrying about the fundamental ideas and which ideas are good, which ideas are not good. Just focus on that and let the ideas speak for themselves eventually. It's like the way machine learning was in the 80s and 90s and whatnot, right? They built the ideas, and now they think they're bearing fruit. Hopefully someday cryptocurrencies will actually work well in practice, and hopefully our ideas will bear fruit.
Yeah, I was about to ask the same questions, that do you think that cryptocurrency will be in the practice like, like other currencies? And because so that's what my next question actually.
I don't know actually, and in a way I'm agnostic to which what actually happens, right? For the very reason that I just mentioned, I want to focus on ideas, because again, focusing on cryptocurrency is also slightly short-sighted, because that's not the only application. You want to build a society that is, I mean, like the ideal. I mean, of course, the social scientists will have to decide whether it's truly ideal or not. But from my point of view, what would be nice is if there can be like a fabric, a decentralized fabric where people can participate in, and applications can run in a completely decentralized manner with proper law enforcement and things like that, but still confidentiality being preserved and whatnot. All the nice properties and scalable, and without. I mean, right now Bitcoin spends the energy equivalent of developed countries like Austria and Switzerland and things like that. So we want it to be much more efficient than that. At some point, it's no longer just going to be a sort of an elite thing. It should percolate like the way internet is percolated throughout humanity. Only then it's actually of much value. And until then, whether it happens or not, I do not know. But the concepts are fun. I'm in it because the concepts are fun, challenging, and keeps me interested.
Yeah, of course, all the researchers have different, all the researchers have this view, and business community has a different view. But yes, definitely, yeah, it will take some time to be in the practice. So there's one more question. With cryptographic assumption in case of Byzantine agreement, what is the best communication and round complexity we possesses?
So with cryptography in place, you can go up to n over 2. I mean, as long as you are just shy of n over 2 bad notes, you can handle it. In terms of the complexities, I need to check. I'm not immediately familiar, but there's been a lot of work with, the problem is there are other parameters. Okay, is it what sort of communication parameters and things like that? Minor differences will start to impact. So I don't expect one paper to have the answer here. You have to it'll be a landscape of results that you'll have to explore to understand it.
So thank you so much, Professor John, for your valuable time and explaining beautifully about the Byzantine agreement, and discuss about all the dimensions and algorithms. I'm really happy to have you here, and Thank you so much, audience, for interesting question. And I appreciate for your constant support to Crypto Innovation Series. So we
Thank you
will
very
come up
much.
with more interesting sessions in Crypto Innovation Series. So stay tuned for the next exciting part of the CIS. Until next time, stay safe, stay secure. This is Shravani signing off. Thank you, Professor.
Thank you very much. Thank you, Shravani, for inviting me, and stay safe, everybody. Thank you.
Yeah.